Alright, let's talk about the interval of convergence of a power series, okay? Now, note that for a power series whose radius of convergence is r, the previous result, the one that we saw in the first video, says nothing about the convergence at its endpoints. So guys, if you end up getting an interval, say x is between 1 and 3, we know for sure that in that case the series is convergent for all values of x between 1 and 3, but we don't know what's happening to the series at x equals 1 or at x equals 3. In other words, we don't know about its convergence or divergence at the end points of the interval. Because if you actually plug in the end points into the limit would be exactly 1, and you know by the ratio test is inconclusive if the limit of the ratio is exactly 1. So we have to do some other test for each endpoint to determine convergence or divergence. Okay, each endpoint must be tested separately for convergence or divergence. Alright guys, so today we are going to talk about the interval of convergence. The interval of convergence of a power series can take any one of the 6 forms. If the series is convergent only at its center, then the radius is 0. If the series is convergent on the entire real number line, then the radius is infinity. Or it could be that the series is convergent on an interval of x values. It could be that it's open and open, open and closed, closed and open, or closed and closed. You see what I mean? So it could be that it's an open interval, half open, half closed, half open, and or it's a closed interval. So the interval of convergence can take any one of these 6 forms. Alright guys, let's do this problem. Now, let me tell you, finding the center of a power series is very easy. Finding the radius of convergence of a power series is just as easy. What can take you some time is determining the interval of convergence. You still have to go through all the work that you do for the radius of convergence by using the ratio test, but you have to do some extra work also. You have to check the endpoints of the interval. Okay, find the interval of convergence of this power series. Alright, now what is the center here? Okay, center is 0, right? X minus 0 to the power n. Okay, so for x not equal to 0, do the ratio test, because we need to know for what other values of x the series converges, right? Alright, how does the ratio test go? Limit as n goes to infinity of the ratio of an plus 1 over an. That's limit as n goes to infinity, x to the power n plus 1 over n plus 1 divide by an, flip it and multiply. Okay, so what do you get? So guys, let's simplify. This is limit as n goes to infinity. We see an extra x in the numerator, right? This is n plus 1, this is n. You see an extra x in the numerator. And then you have n over n plus 1. Okay, so now, what is the limit of this? Well, limit of x does not change, but x must stay inside absolute value signs. Limit of that fraction is 1. So guys, the limit of the ratio is absolute value of x. Okay, what does the ratio test tell you? The ratio test tells us that a series is convergent if the limit of the ratio is less than 1, right? So the limit of the ratio is absolute value of x in this case. So what I'm going to say is series converges when the limit of the ratio, in this case it's absolute value of x, when that is less than 1. So that's going to tell you x is between -1 and 1. So guys, we know for sure this power series is convergent for all values of x between -1 and 1. Okay, not convergent for any value of x less than -1 or not convergent for any value of x bigger than 1. The question is, what can you say about the convergence of this power series at the end points of this interval? Okay, when x is -1, what is the limit? Absolute value of -1, which is 1. We know that the ratio test is inconclusive when the limit is 1. When x is 1, the limit of the ratio is still 1. So the ratio test is inconclusive. So we are not able to say anything about the convergence or divergence of the power series at the endpoints using the ratio test. So we have to do some other tests to determine what's happening at the endpoints. So guys, check endpoint convergence. Okay guys, how do we check? You go ahead and plug in x equals -1 in the original series. When x is -1, let me scroll back up to show you where you have to plug in, guys. So when x is -1, this is where you're going to plug in. Okay, replace x by -1 in the series. So when x is -1, you have sigma n equals 1 to infinity -1 to the power n over an. You know that this is an alternating series, right? With an equal to 1 over n. Remember, an is the part without the alternating component. So guys, because this is an alternating series, to determine the convergence or divergence of this series, let's do the alternating series test. So I'll say do AST. Remember, in order to determine whether a series is convergent or divergent by an alternating series test, you must check two conditions, right? So you have limit as n goes to infinity of an, and that limit must be 0, guys. What's the limit of 1 over n as n goes to infinity? That is 0. The first condition is met. Then you are going to ask, is an plus 1 less than or equal to an for all n? Okay, an is 1 over n. What's an plus 1, guys? 1 over n plus 1. How did I get that? This is my an. To find an plus 1 for this alternating series, replace n by n plus 1. Is that less than or equal to 1 over n? Yes. So guys, this series satisfies both those conditions. So what do we know? So the power series converges at its left-hand endpoint, converges at x equals -1. But don't forget, we must now check the right-hand endpoint. Okay? Next, when x is 1. Okay, when x is 1, go to the original series, guys, and replace x by 1. So 1 to the power n over n. Let me scroll back up here, guys. I'm going to the original series here, replacing x by 1 there in the highlighted part, right? Okay, now you can simplify this. This is going to be n equals 1 to infinity 1 over n. Guys, isn't this a p-series, guys? This is a p-series with p-value equal to 1. Is it convergent or divergent? Okay, p-series with p-value equal to 1 is divergent by the p-series test. Okay, so guys, we checked both endpoints. It turns out that at x equals -1, the power series is convergent. At x equals -1, earlier we did the alternating series test. Now here we did the p-series test, because when we plugged in 1 for x, the power series turned into a p-series with p-value equal to 1. So it's a divergent p-series. Alright. So guys, finally, we would write the interval of convergence for the original series in question. Original series is sigma n equals 1 to infinity x to the n over n. The interval of convergence for the original series in question is, come back here. We know that it was convergent for all x between -1 and 1. When we tested the endpoints, we came to the conclusion the series was convergent at x equals -1 and then divergent at x equals 1. So take the interval from -1 to 1, convergent at -1, put bracket, divergent at 1, put parentheses. This is the interval of convergence. So we call this a half-closed, half-open interval. Alright guys, find the interval of convergence of this power series. Okay, so what is the center here? Center is x equals -1, right? Or you can say c equals -1 to make it very clear. It doesn't matter. Alright guys, so let's start with the ratio test. Okay, I'll say for x not equal to -1. We know that when x is -1, the series converges, right? So let's go ahead and figure out where else this one converges. Okay, so let's start with the ratio test. Do a ratio test. So I'll say limit as n goes to infinity of the ratio -1 to the n plus 1 x plus 1 to the n plus 1 over 2 to the power n plus 1. That's your an plus 1. Divide by an, so flip and multiply by that fraction. Okay, so that's going to be limit as n goes to infinity of, where you have an extra -1 in the numerator, and you have an extra x plus 1 in the numerator, and you have an extra 2 in the denominator. Are you guys able to see how we are determining that? Okay, look, for the x plus 1, the numerator power is n plus 1, the denominator power is n. Numerator power is larger than the denominator power by 1. And for the 2's, the denominator power is larger than the numerator power by 1. Alright guys, now look. What I can do is -1 over 2 when absolute value is 1/2. That's a constant. So let me rewrite this as limit as n goes to infinity of, this is going to be 1/2. I can't take the x plus 1 outside the absolute value signs only because we don't know what x is. Have a look at this guys. This limit does not, 1/2 times absolute value of x plus 1 does not have any n. So the limit as n goes to infinity is going to be 1/2 times the absolute value of x plus 1. So guys, what we have here is that the limit of the ratio by the ratio test is 1/2 times absolute value of x plus 1. And we can say the series converges when the limit 1/2 times absolute value of x plus 1 is less than 1. Remember what the ratio test tells you? Ratio test tells you the series converges when the limit of the ratio is less than 1. Okay, so in order to determine the values of x for which the series converges, you have to start off by setting the limit of the ratio to less than 1. Alright, so solve this absolute value inequality. You have some algebra to do. Let's multiply both sides by 2. Okay, so the 1/2 disappears, right hand side becomes 2. And because you are multiplying by a positive number, there is no reversal in the sign of the inequality. Now, remove the absolute value signs by sandwiching x plus 1 between -2 and 2. Solve this double inequality by subtracting 1 from both sides. So this tells you x must be between -3 and 1 in order for the series to converge. Okay, what you can say is the series is definitely divergent for all values of x less than -3. The series is definitely divergent for all values of x bigger than 1. What can you say about the endpoints? So guys, you have to worry about those endpoints. Okay, when x is -3, go back to the limit of the ratio. -3 plus 1 is -2. When your absolute value is 2, 1/2 times 2 is 1. Ratio test is inconclusive. Similarly, guys, when x is 1, the limit turns out to be 1. Ratio test is inconclusive. You must do endpoint check. So I will say check endpoints. You must check each of these 2 endpoints. Alright, so I'm going to start with when x is -3. Alright guys, let's go to the series. Let me scroll back up a little bit. Okay, let's go to the series. In the series, guys, wherever you see an x, replace it by -3. Okay? So n equals 0 to infinity, right? N equals 0 to infinity. Negative 1 to the power n, x is replaced by negative 3 plus 1 to the power n over 2 to the power n. What is that going to be? Sigma n equals 0 to infinity, negative 1 to the power n, negative 2 to the power n over 2 to the power n. Alright guys, how can we simplify this? Now look, we can use some algebraic properties for this, can't we? Let me recap something, guys. From algebra, let me recap that in this corner. A to the n times b to the n. Isn't that a, b, parenthesized to the power n? Right? So if you are multiplying with like exponents, you multiply the bases and then you copy the exponent down. Here guys, we are multiplying with like exponents. So what you do is you multiply the bases, negative times negative, that will be positive 2 to the power n over 2 to the power n. Is that right, everyone? And what is that going to be? Sigma n equals 0 to infinity, isn't that going to be 1? So when x is negative 3, guys, the power series becomes a very simple series, summation of 1. Isn't that a geometric series? So this is a geometric series with r equal to 1. Absolute value of r is 1. That implies it's divergent, right? Alright, so the power series diverges at x equals negative 3. Okay, power series diverges at x equals negative 3. Now go ahead and check the right-hand endpoint. The right-hand endpoint is when x is 1. When x is 1, guys, go to the original series and replace x by 1. Okay, so negative 1 to the n. In place of x, put 1 plus 1 to the n over 2 to the n. When you simplify, it's negative 1 to the n, 2 to the n over 2 to the n. They cancel. And this is going to be n equals 0 to infinity, negative 1 to the n. So their common ratio is negative 1. Absolute value of r is 1. This series 2 diverges. Okay, it's a geometric series with common ratio negative 1 that diverges. So let me make a note. Power series diverges at x equals 1. Alright guys, now let me write out the most important part. The interval of convergence for the power series given in question. Summation negative 1 to the n, x plus 1 to the n over 2 to the n is. What's the interval of convergence, guys? Let's go back up here. We got this interval and then we check the endpoints. So power series diverges at x equals negative 3 and the power series diverges at x equals 1. That means the endpoints are not included in the interval of convergence. So it's strictly going to be open interval negative 3, comma 1. Okay, open parentheses, guys. Alright, it's convergent for all values of x between negative 3 and 1. The endpoints are not included. We checked the endpoints. The power series diverged at both of these endpoints. Alright guys, a question that I quite often get from my students is that how come this series is divergent? First of all, it is a geometric series whose common ratio is negative 1, absolute value of that is 1, therefore it's divergent, right? Now, some of you might say, how is that it's divergent? Because when you list the terms, it's going to be 1, then negative 1, then 1, then negative 1. So guys, what's happening is this. One of the necessary conditions for convergence is that the limit of the nth term must approach 0. Okay? So in this case, the limit of the nth term is not approaching 0. It's oscillating. It's alternating actually between negative 1 and 1. That's why This turns out to be a divergent geometric series. Okay. Next one, find the interval of convergence of this. Okay, what is the center here? X equals 0. Okay, for x not equal to 0, in other words, we're trying to find for what are the values of x does the series converge, right? Let's go ahead and say limit. For x not equal to 0, guys, I'm going to find the limit of the ratio. Okay, what I'm going to do the ratio test. So limit as n goes to infinity, I should say, limit as n goes to infinity. The ratio of an plus 1 over an. An plus 1 is x to the power n plus 1 over n plus 1 squared divided by an, flip and multiply. Alright, the limit of the ratio is going to be, notice that we have an extra x in the numerator. Then we can rewrite this as n squared over n plus 1 squared. Okay, we are doing multiplication inside absolute value signs, right guys? Multiplication is commutative. You can write them in any order you like. Alright, what is the limit of x? That's going to be inside the absolute values, right? It's going to be absolute value of x. Now tell me, what is the limit of n squared over n plus 1 squared? Alright guys, the power in the numerator is 2. If you did mental expansion, the power in the denominator is also 2. As n goes to infinity, they both have the same powers. That limit is going to be 1. So what we are going to end up seeing is the limit of the ratio is exactly equal to absolute value of x. Okay, what does the ratio test tell you guys? The series converges, in this case the power series converges when the limit of the ratio, in other words, the limit of the ratio turned out to be absolute value of x. So in other words, we will say the series converges when the limit of the ratio is less than 1, meaning when absolute value of x is less than 1. That makes x between -1 and 1. Okay, so we know for sure the series converges for all values of x between -1 and 1, and center is included there, center is 0. Now when x is -1, the limit is 1. When the absolute value -1, it's 1, so it's inconclusive. When x is 1, the limit is 1, it's inconclusive. That's why we must do different tests to determine endpoint convergence. Okay, so check endpoints. Okay, one by one. So when x is -1, scroll back up a little bit, go to the original power series, replace x by -1. Okay, when x is -1, what are we going to have? Sigma n equals 1 to infinity. Replace x by -1. So guys, what is this? When x is -1, the power series turns into an alternating series. Okay, this is an alternating series with an equals 1 over n squared. Remember, for the alternating series, you do not include the alternating component for the an. So guys, what we are going to do is, we are going to do alternating series test. And you should know by now, for alternating series test, you must check the limit as n goes to infinity of an, limit as n goes to infinity of 1 over n squared, which is 0, and that's one of the conditions needed. And then you should ask, is an plus 1 less than or equal to an? Is it decreasing? What's an plus 1, guys? 1 over n plus 1 squared. Is that less than or equal to 1 over squared? Yes. So both conditions for the alternating series are met. So I would say the power series converges when x is -1. Okay? So the power series converges when x is -1. So you have checked the left-hand endpoint. Now go ahead and check the right-hand endpoint. The right-hand endpoint is x equals 1. Go to the power series and replace x by 1. So x to the power n becomes 1 to the n over n squared. When you simplify that, n equals 1 to infinity 1 over n squared. So guys, isn't this a p-series? the p-value is 2, which is greater than 1. What do we know about a p-series whose p-value is greater than 1? We will say convergent, right? Convergent by the p-series test. Convergent by the p-series test. So what we can say is the power series converges when x is 1. Okay? So guys, we got an interval earlier using the ratio test. This was the interval we got earlier. We checked both of those endpoints separately, and the power series converged at both of them. The series converged when x is -1, and the series converged when x is 1. So guys, what are we going to write? The interval of convergence for the original power series in question, which is n equals 1 to infinity x to the n over n squared. Isn't that the original power series? Yes, it is. The interval of convergence for the original power series is -1, 1. It converged at the endpoint, so please put brackets at the left-hand endpoint and at the right-hand endpoint.